We know that an asymptote is a line that a graph gets very close to at the extreme ends of the graph, and they can be vertical, they can be horizontal, or they can occur on a slanted line. A vertical asymptote can occur where a function is undefined. For vertical asymptotes, the vertical asymptote of a rational function can be found by simplifying the expression algebraically, then saying the denominator equal to 0. The resultant values for x provide us with candidates for vertical asymptotes. So there are possible vertical asymptotes. However, we must then compute the limits of the function from the right and from the left for these x values. These limits will tell us the behavior of the graph on either side of the asymptote. So let's say that we're going to create an asymptote where x is equal to a for a vertical asymptote. Then at least one of the following statements has to be true. So let's start by creating our vertical asymptotes at x is equal to a. We can say that the limit as x approaches a from the right side for f of x is equal to positive infinity. So as I approach a from the right side, my f of x is going to shoot up to positive infinity, and it would look like that. I can say that as it approaches a from the right side, it can approach negative infinity. So I approach a from the right side and it shoots down to negative infinity, looking something like this. I can say that it approaches a from the left-hand side and shoots up to positive infinity, which would look something like this. Or I can say that it approaches a from the left side and shoots down to negative infinity, which would look something like this. Can polynomial functions ever have a vertical asymptote? No. Because polynomial functions are continuous for all values of x. We know they just have that domain of XER. Rational functions can have vertical asymptotes because they have undefined values of x in the domain, which we often refer to as our NPVs, or non-permissible values. For example 2, consider f of x is equal to 1 over x. We're going to use limits to describe the vertical asymptotes and then sketch what is happening for the graph just near the asymptotes. So, if f of x is equal to 1 over x, then we know from that that f has a vertical asymptote at x is equal to 0, based on the non-permissible from the denominator. We know that that's going to happen. If we're applying the limits, Then I'm going to take the limit as x approaches 0 from the right for 1 over x, which is going to give me, if I went 1 over 0.000001 or smaller and smaller and smaller, approaching 0, never actually hitting it, it's going to give me that positive infinity. When I take the limit as x approaches 0 from the left for 1 over x, then that would be at negative 0.000000, whatever it happens to be, and that's going to give me approaching negative infinity. So for the vertical asymptotes here, I know from what I've just seen, at x is equal to 0, or the vertical asymptote, as I try to approach that from the right-hand side, it's going to shoot up to positive infinity. As I try to approach that from the left-hand side, it's going to shoot down to negative infinity. For example 3, consider f of x is equal to 1 over x squared. Use limits to describe the vertical asymptotes and sketch the graph near the asymptote. So if I said that f of x is equal to 1 over x squared, then my domain, or my non-permissibles, is still going to be based on x cannot equal 0. So I'm going to say that the limit as x approaches 0 from the right for 1 over x squared is going to equal, well, if I did like 0.000001 or got a smaller and smaller number, we know that that's going to give me positive infinity. If I take the limit as x approaches 0 from the left for 1 over x squared, then I would be taking negative 0.000001, but because I have to square it, then once again, that's going to make it approach positive infinity. Which means that unlike the 1 over x, when I do it for the 1 over x squared, at that vertical asymptote where x equals 0, when it approaches from the right, it's going to approach positive infinity. When it approaches from the left, it's also going to approach positive infinity. For example 4, it asks us to determine the limit as x approaches 6 for 2 minus 3 over x minus 6 squared. So using my properties of limits, I can say that I'm taking the limit as x approaches 6 for the constant of 2 minus 3 times the limit as x approaches 6 for 1 over x minus 6 squared. Well, the limit of a constant is just the constant. And when I try and take the limit as x approaches 6 for 1 over x minus 6 squared, whether I'm approaching from the left or I'm approaching from the right, we can see that this is approaching positive infinity, which means that 2 minus 3 times positive infinity would just be 2 minus infinity, which we could still just consider negative infinity. Therefore, the limit as x approaches 6 for 2 minus 3 over x minus 6 squared does not exist. If we were to take a look at what this looks like on a graph using our graphing calculators, then we're going to have a horizontal asymptote at y is equal to 2. We're going to have a vertical asymptote at x is equal to 6. And our graph would actually look like this, where when we're trying to solve the limit, it's occurring on that asymptote.